In the year 2008, astronomers pointed the Keck Observatory's powerful infrared telescope toward a seemingly ordinary point in the constellation Sagittarius. What they captured would eventually be recognized as one of the most beautiful and terrifying objects in our cosmic neighborhood. The images revealed an enormous pinwheel of glowing material spiraling outward from a central point, rotating majestically against the darkness of space like some cosmic Catherine wheel frozen in time. This wasn't a galaxy or a nebula. This was the death shroud of a star called WR104, and it might have already killed us. We just don't know it yet. You see, WR104 is located approximately 8,000 light-years from Earth, which means the light we're seeing right now left that star 8,000 years ago, back when humans were just figuring out agriculture and building the first permanent settlements. If WR104 exploded into a supernova last Tuesday, we wouldn't know about it until the year 10,008 CE. But here's the truly unsettling part. If that explosion produces what's called a gamma-ray burst, and if that burst is pointed in our direction, the lethal radiation traveling at the speed of light would arrive at exactly the same moment as the pretty light show. There would be no warning, no time to prepare. Just a sudden, invisible wave of the most dangerous form of energy in the universe slamming into our atmosphere at 300,000 kilometers per second. The star you're looking at right now, in images captured by our most sophisticated telescopes, might already be gone. It might have exploded centuries ago, millennia ago, and that information is currently racing toward us through the void. Every second that passes, that wave front of light and radiation gets 300,000 kilometers closer. This is not science fiction. This is not a hypothetical scenario crafted for dramatic effect. This is a real object in our galaxy that astronomers have been nervously monitoring for over 2 decades, and the more we learn about it, the more reasons we find to be concerned. WR104 belongs to a rare and fascinating class of stars known as Wolf-Rayet stars, named after the French astronomers Charles Wolf and Georges Rayet, who first identified them in 1867. These are not your average stars. These are monsters in their final death throes, and understanding what they are requires us to follow the life story of the most massive stars in the universe. When a star is born with more than about 25 times the mass of our Sun, it lives fast and dies young. Our Sun will burn steadily for about 10 billion years total. These massive stars burn through their nuclear fuel in just a few million years. They shine with incredible luminosity, often hundreds of thousands of times brighter than the Sun. And they burn so hot and so fierce that something remarkable happens. The intense radiation pressure from the star's core literally blows the outer layers of the star away into space. Imagine winds so powerful they're stripping away the star's own atmosphere at speeds exceeding 1,000 kilometers per second. Over time, these stellar winds remove the star's entire hydrogen envelope, exposing the helium core underneath. What's left is a Wolf-Rayet star, a naked stellar core burning helium and heavier elements at temperatures exceeding 30,000 Kelvin, more than 5 times hotter than the surface of our Sun. The star is essentially burning itself alive, consuming its own substance at a prodigious rate while simultaneously hurling that material outward in a continuous stellar gale. Wolf-Rayet stars are rare because they don't last long. Once a massive star enters this phase, it typically has only 100,000 to 500,000 years left before it runs out of fuel entirely and collapses into a supernova. In cosmic terms, that's the blink of an eye. It's like catching a glimpse of someone in the final seconds before they step off a ledge. We know what's coming, we just don't know exactly when. Now, here's where WR104 gets particularly interesting. And by interesting, I mean potentially deadly. This isn't a solitary star, it's a binary system, meaning two stars locked in a gravitational dance around their common center of mass. The primary star is the Wolf-Rayet star itself, weighing in at about 25 solar masses. Its companion is what's called an OB-type star, a massive, hot blue star that's probably somewhere between 10 and 20 solar masses. The two stars orbit each other every 220 days, which is remarkably fast for stars of this size. They're close, cosmically speaking, probably separated by a distance similar to that between the Sun and Venus. As they orbit, the Wolf-Rayet star continuously sheds material in those powerful stellar winds we talked about. But because there's a companion star nearby, that ejected material doesn't blow away symmetrically in all directions. Instead, the companion's gravity shapes the outflow, creating a spiral pattern. Think of it like a rotating garden sprinkler, except instead of water, it's ejecting ionized gas and dust at speeds of thousands of kilometers per second. And instead of watering your lawn, it's creating a structure hundreds of times larger than our entire solar system. This is the pinwheel that astronomers observed in 2008. The infrared images showed a perfect spiral of glowing material. Each arm of the spiral representing roughly 220 days' worth of ejected material, creating a cosmic fossil record of the binary orbit. By measuring the pinwheel pattern, scientists could determine the orbital period, estimate the masses of the stars, and, most critically, begin to deduce the three-dimensional orientation of the system. Because here's the thing about pinwheels, they have a rotation axis. If you're looking at a pinwheel face-on, you see the spiral pattern clearly. If you're looking at it edge-on, you see something much more compressed and elongated. The appearance of WR104's pinwheel tells us something about our viewing angle, and that viewing angle is absolutely crucial for determining whether we're in danger. To understand why the orientation matters so much, we need to talk about Wolf-Rayet stars and their connection to one of the most violent phenomena in the universe, gamma-ray bursts. For decades, gamma-ray bursts were one of astronomy's greatest mysteries. They were first detected by accident in the 1960s by American military satellites designed to watch for nuclear weapons tests. These satellites kept picking up intense bursts of gamma radiation coming from random directions in space, typically lasting anywhere from a fraction of a second to a few minutes. The bursts were powerful, incredibly powerful, releasing more energy in seconds than the Sun will produce in its entire 10 billion-year lifetime. And they were coming from all over the sky at a rate of about one per day. For years, nobody knew what was causing them. The breakthrough came in the 1990s when astronomers were finally able to pinpoint the locations of some gamma-ray bursts precisely enough to identify their host galaxies. What they found was shocking. These events weren't happening in our galaxy. They were occurring in distant galaxies billions of light years away. The fact that we could detect them at all from such tremendous distances meant that gamma-ray bursts were far more energetic than anyone had imagined. We're talking about explosions so powerful they briefly outshine all the other stars in their host galaxy combined. It would take the Sun burning for its entire lifetime, and then doing it again trillions of times over to release as much energy as a single gamma-ray burst produces in 10 seconds. The question was, what could possibly generate that much energy? The answer appears to be a hypernova, an especially energetic type of supernova produced when a very massive star collapses. Here's how it works. When a star runs out of nuclear fuel, there's nothing left to hold up the outer layers against the crushing force of gravity. The core collapses catastrophically, going from roughly the size of Earth to the size of a city in less than a second. If the original star was massive enough, that collapsed core becomes a black hole. As the black hole forms, the infalling matter doesn't just disappear quietly. It swirls around the black hole in an accretion disk, heating up to billions of degrees and releasing tremendous amounts of energy. Some of that energy gets channeled along the black hole's rotation axis, creating two narrow jets of matter and energy that punch through the star's outer layers at 99.9% of the speed of light. These jets contain a mix of high-energy particles and intense electromagnetic radiation, particularly gamma rays. When the jets break free from the star's surface, they continue propagating outward into space, creating beams of gamma radiation that can remain focused and deadly across thousands or even millions of light years. This is a gamma ray burst. But here's the critical detail. The burst is not emitted in all directions. It's beamed like a lighthouse or a searchlight. The jets are thought to be relatively narrow, perhaps 10 to 20 degrees wide, though the exact width is uncertain and may vary from event to event. This means that for every gamma ray burst we detect, there are roughly 18 others happening that we can't see because their beams aren't pointed at us. A gamma ray burst is like a gun that only fires in two opposite directions, and whether you're in danger depends entirely on whether you happen to be standing in the line of fire. In the early 2000s, astronomers began to suspect that Wolf-Rayet stars might be the progenitors of long-duration gamma-ray bursts. The evidence was circumstantial at first. Gamma-ray bursts tended to occur in galaxies with active star formation, precisely where you'd expect to find massive, short-lived stars. The few gamma-ray bursts that astronomers could study in detail showed spectroscopic signatures consistent with Wolf-Rayet stars. And the theoretical models made sense. A rapidly rotating Wolf-Rayet star collapsing into a black hole would have exactly the right conditions to produce the powerful magnetic fields and rotation needed to generate jets. As this realization dawned on the astronomical community, people started looking at known Wolf-Rayet stars in our galaxy with fresh concern. And WR-104, with its prominent pinwheel structure and relative proximity, became an object of intense scrutiny. If WR-104 is indeed a gamma-ray burst waiting to happen, and if its rotation axis happens to be pointed toward Earth, we could be in serious trouble. The gamma-ray burst would be lethal at our distance, not in the sense of immediately killing everyone on the planet, but in the sense of triggering a mass extinction event that would fundamentally alter life on Earth. And that brings us to the question that has consumed researchers studying this system. Which way is the gun pointing? When astronomers first started analyzing the pinwheel structure of WR-104 in detail, they made a troubling discovery. The pinwheel appeared to be oriented nearly face-on to Earth. If you imagine the orbital plane of the two stars as a flat disk, and the rotation axis as a line perpendicular to that disk, the measurements suggested that this rotation axis was pointed almost directly at us. A 2008 study led by Peter Tuthill at the University of Sydney estimated that the rotation axis was within about 16 degrees of our line of sight. 16 degrees might sound like a decent margin, but when you're talking about a gamma-ray burst that might have a beam width of 10 to 20 degrees, suddenly that doesn't seem like much of a safety buffer at all. The paper was careful to emphasize the uncertainties in the measurement, but the media coverage was less nuanced. Headlines proclaimed that a Death Star was pointed at Earth. Popular science articles explained that WR-104 could explode at any moment and bombard our planet with lethal radiation. Concerned citizens contacted astronomers asking if they should be building underground bunkers. The scientific community found itself in the awkward position of trying to communicate both the genuine uncertainty about the system's orientation and the very real but highly probabilistic nature of the threat. Because here's the thing about astronomy. Measuring the three-dimensional orientation of an object thousands of light years away is incredibly difficult. We can only see the sky in 2 dimensions. Determining which way something is pointing in the 3rd dimension requires indirect methods and assumptions that may or may not be valid. The technique used to estimate WR-104's orientation relies on careful analysis of that pinwheel structure over many years of observations. As the binary system orbits and the pinwheel rotates, astronomers can track how the pattern changes. If the system were edge-on to us, we'd see the pinwheel compressed in one direction, appearing more elliptical than circular. If it's face-on, the pinwheel appears more circular and symmetric. By measuring the precise shape and how it evolves over time, researchers can estimate the inclination angle. They can also use spectroscopy to measure the velocity of the material in the pinwheel. Gas moving toward us shows up blue-shifted, while gas moving away appears red-shifted. The pattern of these velocity shifts provides additional constraints on the system's orientation. But all of these measurements have uncertainties. The pinwheel structure isn't perfectly smooth or symmetric. There are clumps and irregularities. The stars themselves might be slightly ellipsoidal rather than perfectly spherical due to tidal forces, which would affect the material ejection pattern. Atmospheric turbulence blurs ground-based observations. The system is 8,000 light-years away, which means the pinwheel structure, despite being hundreds of astronomical units across, subtends only a fraction of an arcsecond on the sky. For context, an arcsecond is 1/3600th of a degree. The full moon is about 1/800 arcseconds across. We're trying to measure the shape of something that appears smaller than 1,000th the diameter of the moon, and from that measurement, deduce its three-dimensional orientation with enough precision to know whether we're in the firing line of a potential gamma-ray burst. The error bars on these measurements are substantial, typically plus or minus 10 to 15 degrees. This brings us to 2020, when Grant Hill and Peter Tuthill published an updated analysis of WR-104 using data spanning more than 2 decades. With longer temporal baseline and improved analysis techniques, they were able to refine their estimate of the system's orientation. The good news: their new analysis suggested the rotation axis is probably tilted away from Earth by about 30 to 40 degrees. That's significantly more than the earlier estimate of 16 degrees, and it sounds like we might be safe. After all, if the beam is 20 degrees wide and the axis is pointed 30 to 40 degrees away, we should be well outside the danger zone, right? Well, maybe. The problem is that we don't actually know how wide the beam is. The 10 to 20 degree estimate comes from theoretical models and observations of gamma-ray bursts in other galaxies, but there's substantial uncertainty. Some models predict beams as narrow as 5 degrees. Others suggest they could be 30 degrees or more. The beam might not have a sharp edge, but rather a gradual fall-off in intensity, meaning there could be a penumbra of somewhat reduced but still dangerous radiation extending well beyond the main beam. and we don't know which type of explosion WR-1204 will produce. Not all core collapse supernovae make gamma-ray bursts. The star needs to be rotating rapidly, and the collapse needs to produce a black hole rather than a neutron star. WR-104 is in a binary system, which might affect its rotation rate. Tidal interactions with the companion star could have spun it up or spun it down over time. The mass loss from the stellar winds might have carried away angular momentum, slowing the star's rotation, or the system might have formed from the merger of two smaller stars, which would have added angular momentum. We simply don't know the rotation rate of the Wolf-Rayet star itself, and that's a crucial parameter for determining whether it will produce a gamma-ray burst at all. There's also the question of whether the rotation axis remains stable over time. Binary star systems can exhibit precession, where the rotation axis slowly wobbles like a spinning top. The timescale for this precession depends on the masses of the stars and the details of their interaction. If WR-104's rotation axis is precessing with a period of thousands of years, it might currently be pointed away from us but could swing toward us in the future, or vice versa. We've only been observing this system in detail for about 25 years. That's a tiny snapshot of the system's evolution. We're trying to predict the orientation of the gun at the moment it fires based on watching it sit on the table for a few seconds. The uncertainties compound upon each other. We don't know exactly when it will explode. We don't know if it will produce a gamma-ray burst. We don't know the exact beam width if it does. We don't know the precise orientation of the rotation axis. And we don't know if that orientation is stable over time. When you multiply all these uncertainties together, you end up with a probability estimate that has enormous error bars. Some researchers have estimated that there's roughly a 20 to 30% chance that Earth lies within the potential beam path. But that number should be taken with a substantial grain of salt. It could be 5%. It could be 50%. We genuinely don't know. What we do know is this: WR-104 is definitely going to explode. Wolf-Rayet stars in this mass range and at this stage of evolution have no other option. The star has exhausted its hydrogen and is burning helium. Eventually, it will run out of helium and start fusing carbon, then oxygen, then silicon. Each stage progresses faster than the last because heavier elements yield less energy per fusion reaction, so the star has to burn them faster to maintain pressure support against gravity. Silicon fusion produces iron, and iron is the end of the line. You can't extract energy by fusing iron into heavier elements. Once the core is primarily iron, the star has seconds to live. The core collapses, and in the case of a star as massive as WR-104's primary, that collapse almost certainly leads to black hole formation. The explosion is inevitable. The only questions are when and which direction the gun is pointing when it fires. Estimates for WR-104's remaining lifetime vary wildly, from a few thousand years to 500,000 years. That uncertainty exists because we can't directly observe the interior of the star. We see the surface, which is already extremely evolved, having lost its hydrogen envelope entirely. But we can't see how much helium fuel remains in the core or what stage of fusion the star is currently undergoing. It's like trying to determine how much gas is left in a car's tank by looking at the exterior of the vehicle from a distance of 8,000 kilometers. We can make educated guesses based on theoretical models of stellar evolution, but those models depend on assumptions about the star's initial mass, its rotation rate, its magnetic field strength, and the history of mass loss through stellar winds. Small changes in any of these parameters can shift the predicted lifetime by factors of 2 or more. What we can say is that statistically, WR104 is much more likely to explode in the next 100,000 years than in the next 100 years, simply because the Wolf-Rayet phase typically lasts a few 100,000 years and we have no particular reason to think we're observing it in its final moments. But much more likely doesn't mean certain. Supernovae don't operate on a schedule. They don't send out invitations. The star could explode tonight. It could have already exploded 7,000 years ago, and the light and radiation could arrive in another 1,000 years. Or it might dutifully burn for another 250,000 years before finally running out of fuel. The universe is under no obligation to make things convenient for our curiosity or our safety. And that's what makes WR104 such a uniquely unsettling object. It's not a hypothetical threat or a statistical possibility derived from abstract models. It's a real star system that we can photograph and study, sitting there in the constellation Sagittarius, clearly visible to any moderately powerful telescope, just doing its thing, spinning, shedding mass, spiraling toward an inevitable explosion that may or may not be pointed in our general direction. Every night, somewhere on Earth, an astronomer points a telescope at WR104 and captures an image of that beautiful, terrible pinwheel. The light in that image is 8,000 years old. The star itself, in its current state, is hidden from us by the vast gulf of space and time. We're looking at history, not at the present, and somewhere out there in the darkness, the present version of WR104 continues its stellar death spiral, perhaps already in the final stages before collapse, perhaps with eons still to go. We won't know until the light reaches us, and if that light includes a gamma-ray burst pointed in our direction, we'll have about 8,000 years' worth of consequences arriving all at once, traveling at the speed of light, giving us zero time to react. This is the reality of living in a universe where cause and effect are decoupled by vast distances and the finite speed of light. The dangerous events might have already happened. The catastrophe might already be in motion, racing toward us through the dark. Or we might be perfectly safe, and all this concern might be over nothing. Both possibilities are simultaneously true, superimposed on each other, and they'll remain superimposed until that information finally reaches Earth and the wave function collapses into a definite reality. Welcome to Astronomy. Welcome to WR104. Let's imagine for a moment that the worst-case scenario comes true. Let's say that right now, at this very moment, WR104 is in its final seconds before core collapse. The iron core has grown too massive to support itself. Electron degeneracy pressure, the quantum mechanical force that has been holding the core up against gravity, finally fails. The core implodes at 1/4 of the speed of light, collapsing from roughly the size of Earth to the size of Manhattan in less time than it takes to blink. A black hole forms at the center. In-falling matter swirls around it, heating to billions of degrees, and 2 jets of relativistic particles and gamma radiation punch through the star's poles at 99.9% of the speed of light. One of those jets is pointed directly at Earth. The explosion happens. The neutrinos reach us first, flooding through every detector on the planet, triggering alerts at Ice Cube in Antarctica, Super Kamiokande in Japan, and a dozen other facilities. Astronomers have about 3 hours of warning, just enough time to point every telescope in the world at that spot in Sagittarius, and to send out emergency broadcasts. Then the light arrives. For observers on Earth's night side, a new star suddenly appears in Sagittarius, brightening over the course of minutes to rival Venus, then the Moon. It's visible in broad daylight on the day side, a point of white light that shouldn't be there in the blue sky. Amateur astronomers scramble for their telescopes. News networks cut to breaking coverage. Social media explodes with speculation. And then, traveling at exactly the same speed as that visible light, moving in lockstep with the photons that are creating such a beautiful spectacle, comes the gamma-ray burst. The gamma rays hit Earth's upper atmosphere at an altitude of about 30 to 50 kilometers, in the region known as the stratosphere. This is where the ozone layer resides, that thin shield of O3 molecules that absorbs most of the sun's ultraviolet radiation and makes complex life on land possible. When high-energy gamma rays collide with nitrogen and oxygen molecules in the stratosphere, they don't just pass through harmlessly. Each gamma-ray photon carries enough energy to ionize multiple molecules, stripping electrons away and creating a cascade of chemical reactions. The nitrogen molecules, normally stable N2, get broken apart and recombine with oxygen to form nitrogen oxides, specifically NO and NO2. These nitrogen oxides are incredibly effective at destroying ozone. A single NO molecule can destroy thousands of ozone molecules through catalytic reactions before it's finally removed from the atmosphere. The process is devastatingly efficient. Within the first hour of the gamma-ray burst impact, roughly 25 to 50% of the ozone layer on Earth's day side is simply gone, converted into regular oxygen molecules that don't absorb ultraviolet light. The chemical reactions don't stop when the gamma-ray burst ends. The nitrogen oxides remain in the stratosphere, continuing to eat away at ozone molecules. Atmospheric circulation carries them from the day side to the night side, spreading the destruction globally. Within 24 hours, the ozone depletion has become planet-wide. Within a week, best-case estimates suggest we've lost 30% of our total ozone layer. Worst-case estimates suggest 50% or more. The exact numbers depend on the intensity and duration of the gamma-ray burst, but even the optimistic scenarios are catastrophic. Now, here's what that means on the ground. Ozone absorbs ultraviolet light in the UVB and UVC bands, wavelengths between about 280 and 315 nanometers. Without ozone, this radiation reaches the surface at full strength. UVB intensity increases by a factor of 50 or more in the most heavily affected regions. UVC, which is normally completely blocked and never reaches the surface at all under natural conditions, starts making it through. These are incredibly damaging wavelengths. UVC is so energetic that it breaks chemical bonds in DNA and RNA directly. It doesn't just cause mutations that might lead to cancer decades later. It straight up destroys genetic material on contact. Any living cell exposed to significant UVC radiation for more than a few minutes will die. UVB is somewhat less energetic but still extremely dangerous, causing rapid DNA damage, protein degradation, and cellular death with sufficient exposure. Under normal circumstances, you can get a mild sunburn after 15 or 20 minutes in direct midday sun if you have pale skin. After a major gamma-ray burst has depleted the ozone layer, you'd get a severe sunburn in under 5 minutes. Your skin would start blistering within 15 minutes. Prolonged exposure would cause third-degree burns, but it gets worse because humans can go indoors or cover up. Most of the biosphere can't. Let's start with the oceans. Phytoplankton are microscopic photosynthetic organisms that drift in the upper layers of the ocean, typically in the top 100 meters where sunlight penetrates. They're responsible for producing roughly 50% of Earth's oxygen through photosynthesis. they're also the base of the marine food chain. Everything from krill to fish to whales depends ultimately on phytoplankton. These organisms are exquisitely sensitive to ultraviolet radiation because they live right at the surface where they need to catch sunlight for photosynthesis, but they have minimal protection. Many species have evolved some UV tolerance under natural conditions, but a 50-fold increase in UVB and the sudden appearance of UVC at the surface is beyond anything they can handle. Phytoplankton begin dying en masse within days of the gamma-ray burst. The die-off starts in tropical and subtropical regions where the sun is most intense and spreads toward the poles over weeks and months. You could watch it happen from space. Satellite imagery of ocean color, which normally shows the green tint of chlorophyll from healthy phytoplankton, begins to shift toward blue and brown as vast swaths of ocean turn into biological deserts. The phytoplankton die-off triggers a cascade up the food chain. Zooplankton, the tiny animals that eat phytoplankton, begin to starve. Their populations crash within weeks. Small fish that eat zooplankton follow shortly after. Larger fish that eat smaller fish are next. The entire marine ecosystem begins to collapse from the bottom up. Fisheries fail completely. Coastal communities that depend on fishing for food and income face immediate crisis. But the ecological consequences extend far beyond humans. Seabirds, marine mammals, everything that depends on the ocean for food faces starvation. Penguin colonies in Antarctica might die out entirely. Whale populations would crash. Coral reefs, already stressed by warming oceans, face the complete loss of the zooplankton that corals feed on, leading to rapid reef death on a global scale. On land, the situation is equally dire, but plays out somewhat differently. Plants can't move indoors or hide from the sun. They're rooted in place, and most terrestrial plants rely on photosynthesis, which means they need to expose leaf surfaces to sunlight. Those same leaves are now getting bombarded with UV radiation at levels they never evolved to handle. UVB and UVC damage the photosynthetic machinery inside plant cells, particularly the chloroplasts and the enzymes involved in converting light into chemical energy. Plants start showing signs of stress within days. Leaves develop white or brown patches where cells have died from radiation damage. Growth rates plummet as the plants divert energy toward repairing UV damage rather than growing. Many plants simply can't keep up with the rate of damage and begin to die. Crops are hit especially hard because most domesticated crop plants have been bred for yield and growth rate, not for UV resistance. They're optimized for the UV environment that existed before the gamma-ray burst, and they have no capacity to adapt quickly. Wheat, rice, corn, soybeans, all the staple crops that feed billions of people, begin to fail in fields worldwide. Even if farmers could somehow shield the crops, which is completely impractical at agricultural scales, there's another problem: pollinators. Bees, butterflies, and other insects that pollinate crops are catastrophically vulnerable to UV radiation. Insects have exoskeletons that provide some protection, but their eyes are extremely UV sensitive, and many flying insects navigate using UV cues from flowers. With UV levels 50 times higher than normal, insects start going blind, becoming disoriented, and dying from radiation exposure. Bee colonies collapse. Butterfly populations crash. The plants that survive the UV radiation can't reproduce because there's nothing left to pollinate them. Agricultural systems that depend on animal pollination, which includes about 75% of all crop species, face complete failure. Then there are the forests. Trees are somewhat more resilient than annual plants because they have thick bark that provides some UV shielding, and many tree species have waxy coatings on their leaves that offer modest protection. But protection from normal UV levels doesn't scale linearly. A coating that blocks 90% of normal UV radiation might only block 50% when UV intensity increases by a factor of 50. And that remaining 50% getting through is still far more than the tree can handle. Forest die-offs begin within months, starting with the most sensitive species and spreading to more resistant ones as the months turn into years, and the cumulative UV damage becomes overwhelming. Tropical rainforests, which contain the majority of Earth's terrestrial biodiversity, are particularly vulnerable. The canopy trees might survive initially, but the understory plants that depend on filtered light through the canopy are exposed to far more UV than they can tolerate. They die, which destabilizes the forest structure. Dead plants mean fuel for fires. UV radiation doesn't just damage living tissue. It also breaks down organic compounds in dead plant material, making it drier and more flammable. Fire risk increases dramatically. And once fires start in UV-damaged forests filled with dead vegetation, they spread with unprecedented ferocity. We could see forest fire seasons that make recent catastrophic fire years look mild by comparison. The Amazon could burn. The Congo Basin could burn. Boreal forests in Canada and Russia could burn. The smoke from these fires would create its own climate effects, blocking sunlight and cooling the planet, which ironically might provide some temporary relief from the UV problem as particulates in the atmosphere absorb and scatter UV radiation. But this is a cure worse than the disease, because massive smoke injection into the stratosphere would severely disrupt global climate patterns and worsen the agricultural collapse. Now, let's talk about what this means for humans specifically. The immediate danger is to anyone outdoors when the UV levels spike. People would start experiencing severe sunburns within minutes. Eyes would be damaged through a condition called photokeratitis, essentially a sunburn of the cornea, which is excruciatingly painful and causes temporary blindness. Long-term exposure would lead to cataracts and permanent vision damage. Skin cancer rates would skyrocket, though frankly, cancer is the least of our worries in this scenario because it takes years to develop and most people wouldn't survive that long. The real threat is the collapse of food systems. With crop failures across the board, fisheries gone, and pollinator populations decimated, global food production would drop by 50% or more within the first year. Countries that are currently food exporters would stop exporting to conserve supply for their own populations. Countries that depend on food imports would face immediate famine. We're talking about billions of people suddenly facing food insecurity. Even wealthy nations with food reserves wouldn't be immune because those reserves are typically only sufficient for a few months, and there would be no harvest coming to replenish them. Governments would implement rationing, but rationing only extends the timeline. It doesn't solve the underlying problem that we can't grow food in sufficient quantities anymore. Urban populations would be hit first and hardest because cities depend entirely on food being transported in from rural agricultural areas. If the rural areas aren't producing food, the cities starve. We'd see mass migration from cities to rural areas as people desperately try to find food. This would lead to conflicts over remaining resources, breakdown of social order, and collapse of institutions. And this is all happening against a backdrop of ecological devastation that makes it nearly impossible to rebuild. The medical infrastructure would be overwhelmed immediately. Hospitals would fill with people suffering from UV exposure. Everything from severe burns to eye damage to UV-induced immune suppression that makes people vulnerable to infections. Medical supply chains would break down as global trade collapses. Antibiotics, chemotherapy drugs, insulin, all the medications that require sophisticated manufacturing and global supply chains would become unavailable. Surgeries would become far more dangerous without reliable access to antibiotics. Simple infections that are easily treatable today would become life-threatening. Clean water systems would fail in many areas because water treatment plants require electricity and chemicals that are no longer being produced or distributed. Waterborne diseases would spread. Sanitation would deteriorate as infrastructure breaks down. We'd see the return of diseases that were thought to be controlled or eliminated. Cholera, typhoid, dysentery, all would make comebacks in populations weakened by malnutrition and lacking access to clean water or medical care. Population would decline rapidly, not primarily from the direct effects of UV radiation, though those would claim many lives, but from starvation, disease, and violence, stemming from resource scarcity. Best-case estimates, which assume some level of coordinated international response and adaptation, suggest global population might decline by 30 to 50% over the course of a decade. Worst-case estimates suggest human population could fall by 90% or more, potentially dropping to levels not seen since before the agricultural revolution. We're talking about the potential collapse of industrial civilization and a return to subsistence living for whatever population manages to survive. But here's the truly insidious part. The ozone layer doesn't just snap back quickly. Ozone is constantly being created and destroyed in the stratosphere through natural chemical cycles. Under normal conditions, production and destruction balance out, maintaining a stable ozone layer. But after a gamma-ray burst has created vast quantities of nitrogen oxides and depleted the ozone, it takes time for those nitrogen oxides to be removed from the stratosphere. They gradually react with other compounds and get transported down into the lower atmosphere where they're washed out by rain. But this process takes years. Some estimates suggest it could take 5 to 10 years for nitrogen oxide levels to drop sufficiently that ozone can begin recovering. During that entire time, UV levels remain elevated, continuing to damage ecosystems and making agriculture nearly impossible. Even after nitrogen oxides decline and ozone begins to recover, the recovery process itself takes time. The ozone layer might not return to pre-burst levels for decades. So, we're looking at a decade or more of elevated UV radiation severe enough to prevent normal agricultural activity and cause ongoing ecological damage. This creates a chicken and egg problem. We need functioning ecosystems, particularly phytoplankton in the oceans, to produce the oxygen and organic compounds that help remove nitrogen oxides from the atmosphere. But the ecosystems can't recover while UV levels remain high, and UV levels can't drop until the ecosystems recover enough to help remove the nitrogen oxides. There's a very real possibility of a stable alternative state, a new equilibrium where Earth has a permanently depleted ozone layer, permanently elevated UV levels, and a much simpler, less productive biosphere. Instead of the lush planet covered in forests and teeming with diverse life that we currently inhabit, Earth might end up looking more like Mars did 3 billion years ago when it still had liquid water, but had already lost most of its atmosphere to solar wind stripping. a planet technically capable of supporting some microbial life in protected niches, but largely sterile on the surface. The atmospheric effects don't stop with ozone depletion. The nitrogen oxides created by the gamma-ray burst would also act as greenhouse gases, trapping heat in the atmosphere. Simultaneously, the loss of phytoplankton means a dramatic reduction in CO2 absorption from the oceans. Combined with potential releases of carbon from dying forests and thawing permafrost, we could see a spike in atmospheric CO2 levels. But here's where it gets weird. The nitrogen oxides also form the brown smog in the stratosphere, a layer of light-absorbing particles that would block some percentage of sunlight from reaching the surface. This creates competing effects. More greenhouse gases warming the planet, but less sunlight reaching the surface to warm it. The net effect is uncertain and would depend on the specific concentrations of various compounds in the atmosphere. Some climate models suggest a net cooling effect of 2 to 3 degrees Celsius globally, which might sound pleasant until you realize that a 2 to 3 degree drop in global average temperature is enough to trigger the growth of ice sheets and potentially initiate a slide into ice age conditions. Other models suggest the greenhouse effect wins out, and we get warming instead. The uncertainty is enormous because we're talking about chemistry and physics in a regime that Earth's atmosphere hasn't experienced in hundreds of millions of years. We don't have good data. We don't have natural experiments to calibrate our models against. We're extrapolating from laboratory experiments and theoretical calculations, which is inherently uncertain. What we can say with confidence is that the climate would change dramatically, and not in ways that benefit the remaining human population or ecosystems. Whether it gets warmer or colder, wetter or drier, the change would happen too fast for most species to adapt, and would add yet another layer of stress to ecosystems already on the brink of collapse from UV damage and food chain disruption. There would be some refugia, places where life might persist and potentially begin recovery. Deep ocean ecosystems, particularly around hydrothermal vents where life doesn't depend on photosynthesis, would be largely unaffected by UV radiation. Cave systems would protect organisms from UV exposure. High-latitude regions where the sun is lower on the horizon and UV intensity is somewhat reduced might fare better than tropical regions. Humans who manage to create UV-shielded environments, essentially living indoors or underground with artificial lighting for growing food, might survive in small numbers. But these refugia would be isolated islands in a largely hostile biosphere, and whether they could eventually recolonize the surface would depend on how long the ozone depletion lasts and how much genetic diversity remains after the bottleneck. The comparison that keeps coming up in the scientific literature is the Ordovician mass extinction, which occurred approximately 450 million years ago and resulted in the loss of about 85% of all species. The Ordovician extinction happened in 2 pulses over about 1 million years, and has long puzzled paleontologists because there's no clear evidence of the usual mass extinction triggers like massive volcanism or asteroid impact. But in 2003, researchers proposed that a gamma-ray burst might have been responsible. The evidence is circumstantial but intriguing. Isotope ratios in rocks from that period suggest a dramatic increase in ultraviolet radiation reaching Earth's surface. There are extinctions patterns consistent with UV damage, particularly among surface-dwelling marine organisms, while deeper water species fared better. The timing matches up with a rapid climate shift toward glaciation. None of this proves a gamma-ray burst was responsible, but it's consistent with that hypothesis, and it gives us a geological precedent for what we're discussing. If a gamma-ray burst hit Earth 450 million years ago, it caused one of the 5 largest mass extinctions in our planet's history. Life recovered, obviously, because we're here to talk about it. But recovery took millions of years, and the biosphere that emerged after the extinction was fundamentally different from what came before. The dominant species changed. Ecological structures changed. Evolution took a different path than it would have if the extinction had never happened. That's what we're talking about here. Not just a catastrophe that kills a lot of people and disrupts civilization for a few years before we rebuild. We're talking about a resetting of the evolutionary clock, a pruning of the tree of life that eliminates entire branches and leaves only a few hardy survivors to repopulate a damaged world. And we have no way to prevent it. If WR-104 explodes tomorrow and sends a gamma-ray burst our way, the radiation will arrive before we know the explosion happened. There's no time to evacuate, no shelter that would protect the majority of the population, no technology we could deploy in a few hours that would shield the atmosphere from gamma rays traveling at light speed. We could potentially take some measures if we had years or decades of warning, like deploying massive orbital sunshades to block UV radiation after the ozone is gone, or building underground agricultural facilities lit by artificial light, or developing UV-resistant crop varieties through genetic engineering. But we don't have years or decades. We have zero warning, because the warning and the impact arrive simultaneously. The only reason we're discussing WR-104 at all is because we can see it sitting there in the sky right now, visibly in its death throes, and we can calculate that it has the potential to produce a gamma-ray burst, and we can measure its orientation well enough to know that we might be in the danger zone. But that knowledge doesn't give us the ability to do anything about it except worry and hope that we're not actually in the line of fire. This is the cold, indifferent reality of living in a universe where catastrophically energetic events happen regularly, and by sheer chance might be aimed in our direction. The universe doesn't care about us. It doesn't know we exist. Stars explode when they run out of fuel, and if their jets happen to be pointed toward a planet with billions of years of accumulated evolutionary complexity, and 7 billion humans living out their lives, that's just bad luck. There's no malice, no intent, no meaning, just physics and probability. And right now, that probability is uncomfortably non-zero. So here we are, faced with this uncomfortable question that keeps astronomers awake at night. Is WR-104 pointed at us or not? The answer should be straightforward. We can see the system. We can measure it. We have decades of observations from multiple telescopes. Surely we can figure out which way it's oriented, right? Well, yes and no. The problem with astronomy is that we're trying to reconstruct three-dimensional reality from two-dimensional observations, and we're doing it across distances so vast that the objects we're studying appear impossibly small even to our most powerful instruments. When you look up at the night sky, everything appears projected onto the celestial sphere, that imaginary dome overhead. You can measure the angular position of objects, how far apart they appear, but you can't directly measure their distance or which direction they're facing. Distance requires clever indirect methods like parallax or standard candles. Orientation requires even more inference and assumption. In the case of WR-104, astronomers have been using every trick in the book to nail down that rotation axis, and the more data they collect, the more complicated the picture becomes. Let's start with those early observations from 2008 that first raised alarm bells. Peter Totehill and his team at the University of Sydney had been monitoring WR-104 for several years, using the Keck Observatory's interferometer. an interferometer combines light from multiple telescopes to achieve angular resolution far beyond what any single telescope could manage. This allowed them to resolve the pinwheel structure in exquisite detail, watching it rotate and evolve over time. By measuring the shape of the pinwheel, they could infer the system's inclination. If you're looking at a rotating disk face-on, it appears circular. As you tilt it away from face-on, it appears more and more elliptical. The amount of ellipticity tells you the inclination angle. Toothill's measurements suggested the pinwheel was nearly circular, which implied they were looking at it close to face-on. Their published estimate put the inclination at around 16 degrees, plus or minus about 10 degrees. That error bar is crucial. It means the true inclination could be anywhere from 6 degrees to 26 degrees based on their data. If it's 6 degrees, we're definitely in trouble. If it's 26 degrees, we might still be in trouble depending on the beam width. The paper was careful to emphasize these uncertainties, but the headline number, 16 degrees, was what stuck in people's minds. News articles ran with it. Science communicators explained that WR-104 might be pointed almost directly at Earth, and the scientific community had to grapple with explaining probabilistic risk to a public that wanted a yes or no answer. The challenge with measuring the pinwheel's shape is that it's not actually a perfect geometric structure. Real astrophysical systems are messy. The material ejected by WR-104 doesn't flow out in a smooth, continuous stream. It comes out in clumps and filaments. The wind from the Wolf-Rayet star varies in strength and direction. The companion star's gravity perturbs the flow in complicated ways. When you observe the pinwheel in infrared light, what you're actually seeing is dust that has condensed out of the hot gas as it cooled while flowing outward. That dust traces the overall flow pattern, but not perfectly. There are gaps where conditions weren't right for dust formation. There are bright clumps where dust condensed particularly efficiently. Trying to fit a geometric model to this messy reality involves making choices about which features to emphasize and which to treat as noise. Different analysis techniques can yield different inclination estimates, even from the same data. And then there's the question of which observations to include. The pinwheel is rotating, so its appearance changes over time. Early observations might show it in one orientation, while later observations catch it in a different phase of rotation. If you're trying to determine the three-dimensional structure, you need to combine observations taken at different times and account for the rotation, which requires knowing the rotation period precisely. But the rotation period itself has to be inferred from the observations. You're solving for multiple unknowns simultaneously, and small errors in one parameter propagate into larger errors in others. Beyond the geometric analysis, astronomers also use spectroscopy to constrain the system's orientation. When you split the light from WR-104 into a spectrum, you can measure the Doppler shifts of various spectral lines. Material moving toward us appears blue-shifted, while material moving away appears red-shifted. By mapping the velocity field across the pinwheel structure, you can infer its three-dimensional orientation. If one side of the pinwheel is strongly blue-shifted and the other side is strongly red-shifted, that tells you it's rotating in the plane of the sky, oriented edge-on. If there's minimal velocity difference across the structure, it's rotating more face-on relative to our line of sight. WR-104 shows relatively small velocity differences across the pinwheel, which is consistent with a face-on or nearly face-on orientation. But here again, there are complications. the measured velocities depend not just on the system's orientation, but also on the actual speeds at which material is flowing outward. If the wind speed is higher or lower than assumed, that changes the interpretation. And the wind speed isn't constant. Wolf-Rayet stars have variable winds that fluctuate on timescales of days to weeks. Some of that variability might be due to rotation of the star itself, with different surface regions having different wind properties. Some might be due to instabilities in the wind itself or interactions with the companion star. Disentangling all these effects requires detailed modeling and more observations than are typically available. Then came the 20x20 reanalysis by Grant Hill and Peter Toothill that updated the inclination estimate to 30 to 40 degrees. This used an expanded dataset spanning more than 2 decades of observations, along with improved analysis techniques. The longer temporal baseline is important because it allows them to track the pinwheel's evolution with greater precision and reduce uncertainties in the rotation period and phase. The improved techniques involved better modeling of the dust distribution and more sophisticated geometric fitting algorithms. Their conclusion was that the earlier estimate of 16 degrees was probably too face-on, and the system is more likely tilted at 30 to 40 degrees from our line of sight. On the surface, this sounds like good news. If the rotation axis is tilted 30 to 40 degrees away from pointing at Earth, and if gamma-ray burst beams are typically 10 to 20 degrees wide, then we should be outside the danger zone. But the devil, as always, is in the details and the error bars. That 30 to 40 degree estimate isn't a precise measurement. It's the central value of a probability distribution that has substantial width. The actual inclination could be 25 degrees. It could be 45 degrees. The uncertainty hasn't gone away. It's just shifted to a somewhat more optimistic range. And here's where things get really uncomfortable. Even if we accept the 30 to 40 degree estimate as accurate, we don't actually know how wide the gamma-ray burst beam will be. The 10 to 20 degree estimate for beam width comes from observations of gamma-ray bursts in distant galaxies and from theoretical models of jet formation. When astronomers detect a gamma-ray burst, they can sometimes observe the afterglow, a longer-lasting emission at longer wavelengths that persists for days or weeks after the initial burst. By studying the afterglow properties and comparing them to theoretical predictions, researchers can estimate the opening angle of the jet that produced the burst. These studies generally suggest opening angles in the range of 5 to 30 degrees, with a typical value around 10 to 20 degrees. But there's huge variation from one burst to another. Some appear to have very narrow jets, perhaps only a few degrees wide. Others seem to have much broader jets or even multiple jets at different angles. The structure of the jet depends on the properties of the progenitor star, its rotation rate, its magnetic field strength, and details of how the black hole forms and accretes material. WR-104 is a specific system with specific properties, and there's no guarantee its gamma-ray burst, if it produces one, will have a beam width in the typical range. It could be narrower, which would make us safer, or it could be wider, which would put us right back in the danger zone, even with a 35-degree inclination. There's also the question of beam structure. Early models of gamma-ray bursts assumed the jets were uniform, essentially cylinders of radiation with sharp edges. More recent simulations suggest the structure is probably more complicated. The jet might have a bright central core with higher intensity, surrounded by a dimmer outer region where the intensity falls off gradually. If that's the case, then the beam width isn't a single number but a profile. And you have to ask, How far out in the profile do we consider it dangerous? The core might be 10 degrees wide, but the extended wings of the distribution might reach out to 30 or 40 degrees with reduced but still substantial intensity. If WR-104 is tilted 35 degrees from face-on, we might be outside the central core but still within the outer wings. The radiation dose would be lower than from a direct hit, but it might still be enough to cause significant ozone depletion and ecological damage. Nobody knows because we've never observed a gamma-ray burst from close enough to map out the detailed structure of the beam. Every gamma-ray burst we've studied has been in another galaxy, millions or billions of light-years away, and at those distances we can only measure gross properties. The fine structure is lost. So we're left making educated guesses about what WR-104's beam might look like, based on models that may or may not accurately represent reality. Then there's the precession question. The rotation axis of WR-104 might not be stable over long timescales. Binary star systems can exhibit precession of their rotation axes due to tidal interactions and other effects. Think of it like a spinning top that wobbles as it spins. The rotation axis traces out a cone over time. For WR-104, the precession period, if it exists, is completely unknown. It could be thousands of years, in which case the current orientation is a good indicator of where it will be pointing when it explodes. Or the precession period could be comparable to the remaining lifetime of the star, in which case the orientation might swing through a wide range of angles between now and the explosion. If the system is precessing, and we happen to be observing it at a moment when the axis is tilted away from us, it might precess back toward us before the explosion occurs. Conversely, if it's currently tilted somewhat toward us, it might precess away and be safely pointed elsewhere by the time it goes off. We have no way to measure this precession directly because it would require observations spanning timescales, much longer than the couple of decades we've been monitoring the system in detail. We can try to infer whether precession is likely based on theoretical models of the system's dynamics, but those models depend on parameters like the star's masses, their separation, and their internal structure, all of which have uncertainties. Some models predict a significant precession. Others predict the axis should be stable. Without longer baseline observations, we simply can't distinguish between these scenarios. Another complication is that we don't actually know if WR-104 will produce a gamma-ray burst at all. Not every massive star that explodes creates a gamma-ray burst. The current understanding is that you need specific conditions. The progenitor star must be rotating rapidly, and the core collapse must produce a black hole rather than a neutron star. If the star isn't rotating fast enough, the jets don't form or are too weak to break out of the stellar envelope. If the collapse produces a neutron star instead of a black hole, you get a regular supernova without the gamma-ray burst. WR-104's rotation rate is unknown. We can observe the orbital motion of the binary system, but we can't directly measure how fast the Wolf-Rayet star itself is spinning on its axis. That rotation rate depends on the star's formation history. If it formed from a single massive star that shed its envelope, it might have retained significant angular momentum and be spinning rapidly. If it formed from the merger of two smaller stars, it could be spinning even faster. But it's also possible that the star has been spun down over time by magnetic braking or by angular momentum loss through the stellar wind. Binary interactions could have either increased or decreased the rotation rate depending on the specifics of tidal coupling. We just don't know, and if the star isn't rotating fast enough, It will explode as a supernova, which will still be visible from Earth and quite dramatic, but it won't produce a gamma-ray burst that threatens our biosphere. We'd be safe, at least from that particular threat. There's also uncertainty about the mass of WR-104's core. If the core mass at the time of collapse is below about 25 solar masses worth of material, it's more likely to form a neutron star. Above that threshold, black hole formation becomes more probable. But the core mass depends on how much material the star has lost through winds over its lifetime, and that's poorly constrained. Wolf-Rayet stars are famous for their intense mass loss, shedding solar masses worth of material every 100,000 years or so. WR-104 has clearly lost its entire hydrogen envelope already. The question is how much of the helium core has been lost as well. More mass loss means a less massive core, which makes neutron star formation more likely and gamma-ray burst formation less likely. Less mass loss means a more massive core, favoring black hole formation and gamma-ray bursts. We can estimate the current mass of the star by observing its luminosity and applying stellar evolution models, but those estimates have error bars of several solar masses, which is enough to make the difference between neutron star and black hole outcomes. So, even setting aside the orientation question, we're not certain that WR-104 represents a gamma-ray burst threat at all. It might just be a regular supernova waiting to happen, which would be spectacular, but not dangerous. Let's talk about what other research groups have found. Several independent teams have analyzed WR-104 using different telescopes and techniques, and not all of them agree. Some observations from the Very Large Telescope in Chile suggested an inclination closer to 45 degrees, which would make us safer. Other observations using adaptive optics on Keck suggested inclinations closer to 20 degrees, which would put us more firmly in the danger zone. Part of the disagreement stems from different analysis methods. Part comes from observing the system in different wavelengths, infrared versus near-infrared versus visible light, which highlights different components of the structure. And part may be due to genuine variability in the system. The pinwheel isn't static. It's constantly being refreshed with new material, and the pattern can change if the wind properties change or if the binary orbit evolves. When you have multiple measurements that don't quite agree, you can either average them together, which gives you a central value but washes out any disagreement, or you can try to understand why they disagree, which often reveals that your model of the system is incomplete. In the case of WR-104, there's ongoing debate about which measurements should be weighted more heavily and how to interpret the discrepancies. There isn't a scientific consensus yet on the precise orientation, and there may not be one until we get better data from next-generation instruments, or until the star actually explodes and we find out the hard way. Some astronomers have tried to estimate the overall probability that Earth is in the danger zone by combining all the available information into a statistical model. They take the inclination measurements with their error bars, combine them with estimates of beam width and their uncertainties, factor in the probability that WR-104 will actually produce a gamma-ray burst versus a regular supernova, and calculate an overall risk. These estimates typically come out in the range of 10 to 30% chance that we're at risk, but those numbers are extremely sensitive to the assumptions that go into the calculation. If you assume a narrow beam width of 10 degrees, the risk drops. If you assume a wide beam of 30 degrees, the risk goes up. If you weight the observations suggesting a 45-degree inclination more heavily, risk drops. If you favor the 20-degree inclination measurements, risk goes up. You can make the probability come out to almost anything you want by choosing which data to trust and which assumptions to make about beam properties. This is frustrating from a public communication standpoint because people want a clear answer. Is it going to hit us or not? And the honest scientific answer is, we don't know, and we probably won't know until it happens or doesn't happen. But the probability is high enough that we can't just dismiss it as negligible, and that's uncomfortable. What makes this even more uncomfortable is that WR104 isn't the only potential threat. There are other Wolf-Rayet stars in our galaxy, other gamma-ray burst candidates, and we don't know the orientations of most of them because they haven't been studied in the same detail. WR104 gets attention because it's relatively close at 8,000 light-years. It has that distinctive pinwheel structure that makes it easy to study, and early measurements suggested it might be pointed at us. But there's a star called WR68A at about 18,000 light-years that's also a gamma-ray burst candidate. Its orientation is less well-constrained than WR104, but some observations suggest it might actually be pointed more directly toward us. It's farther away, so the risk is somewhat lower because intensity falls off with distance, but it's still within the range where a gamma-ray burst would cause serious damage. Then there's a system called APEP, also at around 8,000 light-years, which is a binary Wolf-Rayet system showing even more extreme properties than WR104. APEP's stellar winds are clocked at about 12 million kilometers per hour, the fastest ever measured. The system is clearly in an unstable state and will explode soon by astronomical standards. Its orientation is poorly constrained. We don't know if it's pointed at us. And there are probably other systems we haven't identified yet because they don't have obvious visual signatures like pinwheels, or they're obscured by dust, or they're in regions of the galaxy we haven't surveyed thoroughly. Every one of these systems is a potential threat, and for most of them, we know even less than we know about WR104. The situation with Eta Carinii is slightly less worrying, but still worth mentioning. Eta Carinii is one of the most massive and luminous star systems known, probably containing a star of more than 100 solar masses. It's only 700 light-years away, closer than WR104. It already had a major eruption in 1843, known as the Great Eruption, during which it briefly became the second brightest star in the sky, despite being thousands of light-years away. That eruption ejected material equivalent to several solar masses and created the beautiful bipolar nebula that surrounds the star today. Eta Carinii is definitely going to explode, probably within the next million years, and when it does, it will likely be the brightest supernova visible from Earth in recorded history. The good news is that careful observations of the system's structure suggest its rotation axis is oriented about 135 degrees away from Earth. We're not in the line of fire. The jets, if they form, will be pointed perpendicular to our direction. We'll see the supernova, it'll be spectacular, but we won't get hit by a gamma-ray burst. However, the orientation measurement for Eta Carinii also has uncertainties. It's probably safe, but probably isn't the same as certainly. If the orientation estimate is wrong by 40 or 50 degrees, which is within the realm of possibility given the system's complexity, we might not be as safe as we think. What would we actually see if WR104 exploded and we weren't in the gamma-ray burst path? Let's imagine the best-case scenario where the beam misses us. The first sign would be a neutrino burst detected by underground detectors. Neutrinos are produced copiously during core collapse and escape from the star almost immediately, because they barely interact with matter. The neutrinos would arrive at Earth several hours before the light because they can leave the star's core instantly, while photons take time to diffuse through the stellar envelope. Astronomers would have a few hours warning to point every telescope on the planet at WR 104. Then the visible light would arrive. A new star would appear in Sagittarius, brightening rapidly over the course of hours or days. At 8,000 light-years distance, a supernova would reach peak brightness of about magnitude 10, roughly 100 times brighter than Venus, bright enough to cast shadows at night and be visible in daylight. It would be the brightest stellar event visible from Earth since supernova 1006, which appeared in the year 1006 CE and was visible in daylight for weeks. The supernova would remain visible to the naked eye for months, slowly fading as the ejected material expanded and cooled. Astronomers would have a field day studying it, collecting spectra, tracking the evolution of the light curve, searching for evidence of element synthesis and jet formation. It would be the closest supernova observed with modern instruments, an unprecedented opportunity to test our theories of stellar death. And, as long as we're not in the gamma-ray burst beam, it would be purely scientifically valuable with no danger to Earth. But if we are in the beam, all that scientific excitement would be overshadowed by the dawning realization that we're about to face an extinction-level catastrophe. The neutrino detectors would alert us that something is happening. The visible light would arrive showing us the explosion. And traveling alongside that light, invisible and undetectable until it hits our atmosphere, would be the gamma radiation that's about to change everything. We'd have no time to react, no time to prepare, just a few hours to watch the beautiful death of a distant star and understand what's about to happen to us. So, when exactly is WR 104 going to explode? This is the question everyone wants answered, and it's the one question astronomers absolutely cannot answer with any precision. We know it's going to happen. Wolf-Rayet stars in this mass range and at this evolutionary stage have no other option. The star has burned through its hydrogen, it's currently burning helium in its core, and eventually it will run out of fuel entirely. When that happens, core collapse is inevitable. But the timeline between now and that moment could be a few thousand years, or it could be 500,000 years, and there's simply no way to know which end of that range we're closer to. The problem is that we can only observe the surface of the star. We can see that it's hot, that it's luminous, that it's shedding mass at a tremendous rate. But we cannot see into the core where the nuclear fusion is happening. We can't directly measure how much helium fuel remains, or what stage of burning the star is currently undergoing. It's like trying to determine how much fuel is left in a car's tank by looking at the outside of the vehicle from 8,000 kilometers away. You can make educated guesses based on the model of car and how long it's been driving, but you can't actually see the fuel gauge. Stellar evolution models can give us rough estimates. These are sophisticated computer simulations that track the life of a star from birth to death, calculating how nuclear fusion progresses through different stages and how the star's structure evolves over time. You input parameters like the star's initial mass and chemical composition, and the model spits out predictions for temperature, luminosity, mass loss rate, and remaining lifetime at various stages. When astronomers apply these models to WR 104, using estimates of its current mass around 25 solar masses and its observed luminosity and temperature, the models suggest the star is somewhere in the middle to late stages of helium burning. But here's where the uncertainty explodes. those models depend critically on parameters we don't know precisely. The star's initial mass before it started losing material through winds could have been 40 solar masses or 60 solar masses or even higher. The amount of mass lost over the star's lifetime depends on the strength and duration of the stellar winds, which varies based on the star's rotation rate, magnetic field, and other factors we can't directly measure. If WR-104 has been shedding mass particularly efficiently, it might have already burned through more of its fuel than a less efficient mass loser, which would place it closer to core collapse. If mass loss has been less efficient, more fuel remains. Small changes in these input parameters can shift the predicted remaining lifetime by factors of 2 or 3 or even more. The models also have to make assumptions about mixing in the stellar interior. As fusion proceeds, heavier elements are created in the core. If the star's interior is well mixed, those heavier elements get circulated throughout, which affects the fusion rate and the star's structure. If mixing is inefficient, the core becomes more stratified with heavier elements concentrated at the center. Real stars probably fall somewhere between perfect mixing and no mixing, but exactly where depends on details of convection, rotation, and magnetic fields that are difficult to model accurately. Different assumptions about mixing can change the predicted lifetime by tens of thousands of years. And then there are instabilities and variations that the models might not capture at all. Stars aren't perfectly steady objects. They pulsate, they have surface activity, they experience episodic mass loss events. WR-104 had that great eruption analog back in 1843, where Eta Carinae ejected several solar masses worth of material in a brief period. Did WR-104 have similar eruptions in its past that aren't recorded because nobody was watching? If so, those eruptions would have removed mass and potentially changed the star's evolutionary trajectory in ways the smooth models don't account for. The upshot is that when you run these models and account for all the uncertainties, you get remaining lifetime estimates that span a huge range, typically from about 10,000 years on the short end to 500,000 years on the long end, with no strong reason to favor one part of that range over another. Statistically, if the Wolf-Rayet phase lasts around 100,000 to 500,000 years total, and we have no particular reason to think we're observing WR-104 at a special moment, then the star is probably somewhere in the middle of that range. It's more likely to explode in 100,000 years than in 100 years, just because there are more 100-year intervals within the next 100,000 years than there are within the next 100 years. But that's weak probabilistic reasoning based on the assumption that all moments in the star's Wolf-Rayet phase are equally likely to be observed. If there are observational selection effects, that assumption breaks down. For instance, if stars in the final few thousand years before explosion become more luminous or develop more prominent pinwheel structures that make them easier to detect, then the sample of observed Wolf-Rayet stars might be biased toward ones that are close to explosion. We don't know if such selection effects exist for WR-104 specifically. The pinwheel is certainly prominent and beautiful, which is part of why the system has been studied so extensively. But is it more prominent than other Wolf-Rayet binary systems? And if so, does that mean something about the system's evolutionary stage? Nobody knows. There is one potential source of advance warning, though it comes with a very short lead time. When a massive star's core finally runs out of fuel and begins to collapse, enormous numbers of neutrinos are produced. Neutrinos are nearly massless particles that barely interact with ordinary matter. They can pass through entire planets without being stopped. This means that when they're created in the collapsing core, they escape almost immediately, streaming out through the star's outer layers as if they weren't there. Light, by contrast, is constantly absorbed and re-emitted by the hot, dense material in the star's envelope. Photons take a random walk from the core to the surface, which can take hours or even days for a supergiant star. So, the neutrinos arrive at Earth first, giving us a heads up that the core has collapsed even before the light from the explosion emerges. For supernova 1987A, which exploded in the Large Magellanic Cloud at a distance of about 168,000 light-years, neutrinos were detected by underground detectors about 3 hours before the supernova was visible in optical telescopes. Those few hours gave astronomers time to point instruments at the right region of sky and catch the supernova as it brightened, providing unprecedented data on the early phases of the explosion. For WR-104 at 8,000 light-years, much closer than supernova 1987A, the neutrino flux would be far more intense and easily detectable by current-generation neutrino observatories. Facilities like IceCube in Antarctica, Super Kamiokande in Japan, and several others around the world are constantly monitoring for the distinctive signature of a core collapse supernova neutrino burst. These detectors are sensitive enough that they would immediately recognize the signal from WR-104. Within seconds of the neutrinos arriving, automated alerts would go out to astronomers worldwide. The Supernova Early Warning System, or SNEWS, is a network that coordinates these detectors and distributes alerts when multiple facilities detect a neutrino burst simultaneously, which helps confirm it's real and not a false alarm. If WR-104 collapsed right now, neutrino detectors would light up. SNEWS would send out alerts, and astronomers would have approximately 3 hours, maybe a bit more, before the optical light from the supernova became visible. 3 hours to point every available telescope at that spot in Sagittarius. 3 hours to prepare instruments, clear observing schedules, alert teams. 3 hours of knowing that one of the closest supernovae in modern history is about to become visible. But here's the uncomfortable part. Those same 3 hours would also be all the warning we'd have if a gamma-ray burst is headed our way. The gamma rays travel at the speed of light, same as the optical photons. They're leaving the star at the same time as the visible light, just at higher energies. When the optical light reaches Earth, so do the gamma rays. The neutrinos give us a 3-hour heads up, but there's absolutely nothing we could do in 3 hours to protect the planet from a gamma-ray burst. We couldn't evacuate anyone. We couldn't deploy shields. We couldn't even get most people indoors because 3 hours isn't enough time to communicate an emergency to billions of people scattered across the planet. All we could do is watch and wait and hope that the gamma-ray burst, if there is one, isn't pointed at us. Actually, that's not quite true. There would be one thing we could do. In those 3 hours, scientists could frantically check their models and calculations one last time. They could look at the latest observations of WR-104's orientation, try to refine the inclination estimate, calculate probabilities. They could prepare for what might come next, alerting emergency management agencies, sending communications to world governments, drafting public statements. But realistically, 3 hours is barely enough time to reach consensus on what to say, much less implement any kind of response. By the time the neutrino alert comes, the die is already cast. The gamma rays are either headed our way or they're not, and there's nothing anyone can do to change that outcome. We'd just be waiting to see which version of reality we're living in, and then the light would arrive. Astronomers would see the supernova brighten. Instruments would start collecting spectra. And if we're not in the gamma-ray burst path, we'd have the scientific opportunity of a lifetime to study a nearby core collapse supernova in unprecedented detail. If we are in the path, well, the gamma rays would hit the atmosphere simultaneously with the visible light, and we'd know within hours as atmospheric sensors detected the radiation and the chemical changes in the stratosphere began. By the next day, we'd know for certain whether we'd just witnessed a beautiful but distant stellar death or the beginning of a mass extinction event. Now, WR-104 is not the only Wolf-Rayet star we should be concerned about. There are roughly 500 known Wolf-Rayet stars in our galaxy, and undoubtedly more that haven't been discovered yet because they're obscured by dust or located in regions we haven't surveyed thoroughly. Most of these are too far away to pose a threat. A gamma-ray burst needs to be within about 10,000 light-years to cause serious damage to Earth's biosphere, and the vast majority of Wolf-Rayet stars are much farther than that. But there are a handful of relatively nearby candidates that astronomers keep an eye on, and some of them are arguably more concerning than WR-104. Take WR-68A, for instance. This is another Wolf-Rayet star in a binary system located about 18,000 light-years away in the constellation Centaurus. It's farther than WR-104, so the intensity of any gamma-ray burst would be reduced by a factor of about 5 due to the greater distance, which sounds reassuring until you remember that even a reduced gamma-ray burst is still catastrophically powerful. WR-68A doesn't have the same prominent pinwheel structure that makes WR-104 so photogenic, which means it hasn't been studied in as much detail. But the observations that do exist suggest it might be oriented closer to face-on relative to Earth than WR-104. If that's true, and if WR-68A produces a gamma-ray burst when it explodes, we could be more directly in the line of fire despite the greater distance. The problem is that the orientation measurements for WR-68A are even more uncertain than for WR-104, because we have less data. It's like comparing two guns, where we're pretty sure one is pointed somewhere in our general direction, but we can't quite tell which way the other one is aimed. Both are concerning, but in different ways. Then there's the APEP system, which is in some ways even more extreme than WR-104. APEP is a Wolf-Rayet binary located roughly 8,000 light-years away, about the same distance as WR-104, discovered relatively recently in 2018. What makes APEP remarkable is the sheer violence of the system. It's ejecting material in stellar winds clocked at around 12 million kilometers per hour, the fastest stellar winds ever measured. For context, WR-104's winds are already incredibly fast at a few million kilometers per hour, but APEP is roughly 4 times faster. Those extreme wind speeds suggest the stars are in an advanced evolutionary state and possibly very close to core collapse. APEP also shows a spectacular pinwheel structure, but with a twist. When astronomers analyzed the system, they found something bizarre. The dust pinwheel is rotating at one speed, but spectroscopic measurements of the gas show it's moving at a different speed. The gas is moving much faster than the dust, by a factor of about 4. This mismatch is strange and suggests something unusual is going on in the system's dynamics. One interpretation is that we're looking at the system from an angle that creates projection effects, where the true three-dimensional velocities look different when projected onto our two-dimensional view. If that's the case, it might mean the system is oriented more face-on than edge-on, which would put us more directly in the line of any potential gamma-ray burst. But again, the orientation is poorly constrained because the system is so complex and has only been studied in detail for a few years. APEP might explode before WR104. It might be aimed more directly at us, or it might be oriented safely away, and the velocity mismatch is due to something else entirely. We don't know. Eta Carinae deserves another mention here because even though it's probably not aimed at us, it's so intrinsically interesting and so close that it warrants continued monitoring. At 7,500 light-years, Eta Carinae is closer than any of the other systems we've discussed. It's also far more massive, probably containing a primary star of 100 solar masses or more. Stars this massive are incredibly rare and incredibly unstable. Eta Carinae has had multiple eruptions in recorded history, most famously the Great Eruption of the 1840s when it ejected 10 solar masses worth of material and briefly became one of the brightest stars in the sky. That eruption created the spectacular Homunculus Nebula that surrounds the star today, a beautiful bipolar structure of expanding gas and dust. The cause of the eruption is still debated. It might have been a collision between the primary star and a companion, or an instability in the star's envelope, or something else. Whatever the cause, it demonstrates that the system is highly unstable and capable of dramatic outbursts. The current thinking is that Eta Carinae will explode as a supernova relatively soon, within the next million years or so, and it could happen much sooner than that. When it explodes, it will be by far the brightest supernova visible from Earth in recorded history, probably reaching magnitude 15 or brighter, which is about 10 times brighter than Venus at its brightest. It will be visible in daylight for weeks and cast strong shadows at night. The spectacle will be incredible, and if it produces a gamma-ray burst, the jet orientation matters enormously. Current best estimates based on the structure of the Homunculus Nebula suggest the rotation axis is tilted about 135 degrees relative to our line of sight, meaning the jets would be pointed perpendicular to us. We'd see the supernova from the side, not from directly in front of the jet. That's good news. But those estimates come with error bars, and if the true orientation is different by 40 or 50 degrees, we might not be as safe as we think. There are probably other Wolf-Rayet stars closer than these that we haven't identified yet. Our census of nearby massive stars is incomplete, particularly in the plane of the Milky Way where dust obscures our view. Infrared surveys are helping to find these hidden stars, but it's painstaking work. Every few years, astronomers discover a new nearby Wolf-Rayet star, or a new massive star that will eventually become a Wolf-Rayet star. Some of these discoveries are stars that were always there, but nobody had looked at them carefully before. Others are stars that have recently transitioned into the Wolf-Rayet phase, and suddenly became much more noticeable due to increased mass loss. Each new discovery is a reminder that our catalog of potential threats is incomplete. There could be a Wolf-Rayet star sitting at 5,000 light-years, pointed directly at Earth, and we might not know about it because it's hiding behind a dust cloud or because it's in a part of the sky that hasn't been surveyed thoroughly in the right wavelengths. This is not meant to be paranoid or alarmist, just a statement of fact. The galaxy is big. Our observations are limited, and we don't have complete knowledge of every potential hazard. What about gamma-ray bursts from outside our galaxy? Could one of those hit us? Technically, yes, but the probability is much lower. Gamma-ray bursts are detected from distant galaxies all the time, about once per day on average. But those are happening in galaxies millions or billions of light-years away, and we only detect the ones whose jets happen to be pointed at us by chance. For a gamma-ray burst in a distant galaxy to be dangerous to Earth, it would have to be extraordinarily powerful and extraordinarily well-aimed. At intergalactic distances, the intensity of the radiation falls off so much that even a typical gamma-ray burst would be relatively harmless. You'd need something exceptional, like a hypernova producing an unusually energetic burst, and even then it would need to be in a relatively nearby galaxy, within a few million light-years. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. A gamma-ray burst in Andromeda would need to be pointed almost exactly at us to cause any concern, and even then the radiation would be diluted enough that it probably wouldn't trigger a mass extinction, just elevated UV levels for a while. The Magellanic Clouds, two small satellite galaxies of the Milky Way, are much closer at around 160,000 light-years. A gamma-ray burst in one of the Magellanic Clouds could potentially be dangerous if aimed at us, but those are small galaxies with relatively few stars, so the rate of gamma-ray bursts there is much lower than in the Milky Way. Statistically, we're far more likely to be threatened by a gamma-ray burst from within our own galaxy than from an external source. How often do gamma-ray bursts occur in the Milky Way? This is a crucial question for assessing the overall threat level. Based on the observed rate of gamma-ray bursts in other galaxies, and scaling it to the Milky Way's size and star formation rate, astronomers estimate that our galaxy produces roughly one long-duration gamma-ray burst every 1 to 10 million years. That's the rate at which the events occur, not the rate at which they hit Earth. Since the jets are narrow, maybe 10 to 20 degrees wide, they only cover a small fraction of the sky. If you imagine a gamma-ray burst going off at a random location in the galaxy and pointed in a random direction, the probability that its jet intersects Earth is tiny. The typical estimate is that any given point in the galaxy has roughly a 0.0003% chance of being hit by a gamma-ray burst jet per million years. That sounds comfortingly small until you multiply it out over long timescales. Over the 4.5 billion years that Earth has existed, the cumulative probability of being hit by at least one gamma-ray burst from somewhere in the galaxy is something like 10 to 15%. Not guaranteed, but not negligible either. And if you account for the fact that Earth's ozone layer only formed about 600 million years ago, before which we would have been less vulnerable to UV radiation because life was mostly in the oceans and hadn't yet colonized land, the probability of being hit during the period when it would really matter is maybe 2 to 3%. Still not zero. There's some evidence that Earth may have been hit by a gamma-ray burst in the past. The Ordovician mass extinction, which occurred approximately 450 million years ago, killed off about 85% of all species, and remains one of the 5 largest mass extinctions in Earth's history. The extinction happened in 2 pulses over the course of about 1 million years, and for a long time, paleontologists couldn't figure out what caused it. There was no evidence of massive volcanism, no asteroid impact crater, no obvious climate shift that would explain such a catastrophic loss of biodiversity. In 2003, a team of researchers proposed that a gamma-ray burst might have been responsible. They pointed to several lines of evidence. First, isotope ratios in rocks from that period suggest there was a dramatic increase in ultraviolet radiation reaching Earth's surface, consistent with ozone depletion. Second, the extinction pattern shows that shallow water marine organisms were hit much harder than deep water species, which is exactly what you'd expect if UV radiation was the culprit, since UV doesn't penetrate more than a few tens of meters into water. Third, there was a rapid onset of glaciation around the same time, which could be explained by nitrogen oxide formation in the atmosphere blocking sunlight and cooling the planet. None of this proves that a gamma-ray burst was responsible, and there are alternative explanations for each piece of evidence. But it's consistent with the hypothesis, and it shows that such events are plausible within Earth's history. The Devonian extinction, about 375 million years ago, is another candidate. This extinction also occurred in two pulses and disproportionately affected shallow water organisms, while deep water species fared better. There's evidence of plant species decline on land, consistent with UV damage, and signs of rapid climate change. Again, no proof, but the pattern fits. If these two extinctions were indeed caused by gamma-ray bursts, that would suggest a rate of maybe one dangerous burst hitting Earth every few 100 million years, which is somewhat higher than the statistical estimates would suggest. But it's also possible that we're seeing patterns where none exist, trying to explain ancient catastrophes with dramatic cosmic events when the real causes were more mundane. The honest answer is, we don't know for certain whether Earth has been hit by gamma-ray bursts in the past, but it's plausible, and the consequences would have been severe. Looking forward, when can we expect the next one? Statistically, if the Milky Way produces a gamma-ray burst every 1 to 10 million years, and any given location has a tiny chance of being in the path of the jet, you'd expect Earth to be hit every few 100 million years on average. We're potentially due, in the sense that it's been a couple 100 million years since the Devonian extinction, but due is not how random processes work. The next gamma-ray burst could hit tomorrow, or it could be a billion years from now. The probability doesn't care about when the last one occurred. Every moment has the same tiny probability, and those moments add up over geological time. For perspective, the probability of Earth being hit by a dangerous gamma-ray burst in the next century is something like 0.001%, which is so small it's not worth worrying about in any practical sense. The probability over the next million years is maybe 0.001%, still tiny. It's only when you extend the timescale to tens or hundreds of millions of years that the cumulative probability becomes significant. This is relevant for thinking about the long-term future of life on Earth, and whether intelligent civilizations in the galaxy have to contend with periodic cosmic catastrophes that reset the evolutionary clock. But for anyone alive today, the gamma-ray burst threat from random events in the galaxy is essentially zero. The only reason WR104 is concerning is because it's not a random event. It's a specific star that we know is going to explode soon by cosmic standards, and we know it might be oriented toward us. That takes it out of the realm of statistical background risk and makes it a concrete, identifiable threat that we can worry about in specific terms. Still unlikely to hit us, probably, but not astronomically unlikely in the way that a random gamma-ray burst from some unknown star would be. So, what does WR104 tell us about life in the universe more broadly? This is where we transition from a specific threat assessment about one particular star to larger questions about the prevalence of life, the challenges that life faces, and whether intelligent civilizations like ours are common or rare in the cosmos. These questions fall under the umbrella of what's called the Fermi paradox, named after physicist Enrico Fermi, who famously asked during a lunch conversation in 1950, "Where is everybody?" The paradox is this: the universe is enormous and ancient. Our galaxy alone contains hundreds of billions of stars, many of them billions of years older than the Sun. Even if only a tiny fraction of those stars have planets capable of supporting life, and even if only a tiny fraction of those planets actually develop life, and even if only a tiny fraction of those develop intelligent life, you'd still expect there to be thousands or millions of technological civilizations in the Milky Way. Some of them should be far older than humanity, with millions or billions of years of technological development behind them. Such civilizations would presumably be capable of interstellar travel or at least sending out probes or signals. We should see evidence of them everywhere, but we don't. The sky is silent. We've searched for radio signals, optical signals, infrared signatures of megastructures, anything that might indicate technological activity, and we've found nothing. Where is everybody? There are dozens of proposed solutions to the Fermi paradox, ranging from pessimistic to optimistic, and gamma-ray bursts feature prominently in several of them. One category of solutions involves what's called the Great Filter, a concept popularized by economist Robin Hanson. The idea is that there's some stage in the development of life, from the first organic molecules to galaxy-spanning civilizations, that's extraordinarily difficult to pass through. Most potential civilizations get stuck at this filter and never make it to the next stage. The filter could be behind us, meaning the hard step was getting from non-life to life, or from single-celled organisms to complex multicellular life, and we've already passed it. If that's the case, we're special, and intelligent life is extremely rare in the universe. Or the filter could be ahead of us, meaning most civilizations reach roughly our level of development and then destroy themselves, or get destroyed before they can spread to other star systems. If that's the case, we're in danger, and the silence in the sky is ominous because it means civilizations like ours don't tend to last long. Gamma-ray bursts could be part of a great filter scenario if they occur frequently enough to regularly sterilize planets that are developing complex life. The early universe had more massive stars than today because the initial generation of stars formed from pristine hydrogen and helium without heavier elements. Those first-generation stars were often enormous, dozens or hundreds of solar masses, and they burned out quickly, exploding as supernovae and possibly gamma-ray bursts. The rate of gamma-ray bursts in the early universe was probably much higher than it is today. Any planet trying to develop life in those first few billion years after the Big Bang would have faced a constant bombardment of cosmic catastrophes. Perhaps life could get started, develop simple organisms, even reach the complexity of bacteria or algae. But every few 100 million years, a gamma-ray burst would wipe the slate clean and evolution would have to start over. This would delay the emergence of complex life until the galaxy settled down and the gamma-ray burst rate decreased, which might explain why intelligent life took so long to appear, even though the universe is nearly 14 billion years old. There's a concept called the habitable epoch of the galaxy, the period of time when conditions are suitable for life to develop without being constantly reset by catastrophes. The early galaxy was too violent, with too many supernovae and gamma-ray bursts and collisions between galaxies. The far future will be too quiet, with star formation slowing down and eventually ceasing altogether as the galaxy runs out of gas to make new stars. There's a sweet spot in between, and we might be living in it. The Sun is about 4.6 billion years old. It took roughly 4 billion years for intelligent life to emerge on Earth. If you add those numbers together, It suggests that planets need at least 8 or 9 billion years of relatively stable conditions to go from sterile rock to technological civilization. The universe is 13.8 billion years old, so we're right around the time when the first intelligent civilizations would be expected to appear if our timeline is typical. Maybe we're among the earliest. Maybe the reason the sky is silent is because most civilizations are still in their equivalent of the Stone Age, or haven't evolved yet. This would be good news for us because it means there's no great filter ahead, at least not one that we can see evidence of in the form of dead civilizations. The downside is that it also means we're alone in a profoundly lonely way. There's no one out there to contact, no one to learn from, no one to warn us of dangers or share knowledge with. We're pioneers in a galaxy that's only just becoming habitable for intelligence. But there's also a spatial component to habitability, not just temporal. The galaxy has structure, and some regions are safer than others. The galactic center is a nightmare environment for life. The density of stars is extremely high, which means frequent close encounters, supernovae going off every few thousand years within dangerous range, and an enormous black hole lurking at the very center. Any planet in the inner few thousand light years of the galaxy would face constant bombardment from radiation, and would have its orbit perturbed by gravitational interactions. The outer regions of the galaxy are safer from catastrophes, but have a different problem. They're metal poor. By metal, astronomers mean any element heavier than helium. Planets, and especially rocky planets capable of supporting life, require heavier elements like carbon, oxygen, silicon, and iron. These elements are produced in supernovae and dispersed into the interstellar medium where they get incorporated into new stars and planets. The outer galaxy hasn't had as many generations of star formation and recycling, so there's less raw material for making Earth-like planets. The habitable zone for complex life might be an annulus, a ring around the galaxy where you're far enough from the center to avoid constant catastrophes, but close enough that there are sufficient heavy elements to build planets. Our solar system is located about 26,000 light-years from the galactic center, right in what many researchers consider the optimal zone. Not too hot, not too cold, just right. If most of the galaxy is uninhabitable for one reason or another, that dramatically reduces the number of potential sites where life can develop, which helps explain why we don't see evidence of civilizations everywhere. Gamma-ray bursts fit into this picture as one of the hazards that define the boundaries of the habitable zone. If you're too close to the galactic center where the density of massive stars is high, the rate of gamma-ray bursts is correspondingly high. You might get hit every few tens of millions of years, which is often enough to prevent complex life from ever developing. If you're in the outer galaxy, gamma-ray bursts are rare, but you also don't have the heavy elements needed to build planets in the first place. The sweet spot is in between, in the galactic suburbs where we happen to live. Even here, gamma-ray bursts are a non-negligible threat. We've calculated that Earth has maybe a 10 to 15% chance of being hit by one over its entire history. That's low enough that life can develop, but high enough that it's a real constraint. If you were a civilization planning where to place a colony in the galaxy, you'd want to know the gamma-ray burst rate in different regions and choose accordingly. But emerging civilizations don't get to choose. You evolve where you evolve, and if you're unlucky enough to be in a region with high gamma-ray burst rates, you don't get to develop intelligence before you're wiped out. This acts as a selection effect. The civilizations that do develop are disproportionately located in low-risk regions, which might be relatively rare, which would explain why intelligence is rare even if life itself is common. Now, let's think about what advanced civilizations do in response to gamma-ray burst threats. If you are a technological species aware of the danger, you have options that life arising on a planet doesn't have. You can build underground. You can develop UV-resistant crops and livestock. You can create a technology to regenerate ozone layers quickly after a gamma-ray burst. You can spread to multiple planets or star systems so that even if one gets hit, the species survives elsewhere. A sufficiently advanced civilization might not care about gamma-ray bursts at all because they've engineered their way around the threat. This raises an interesting question about the Great Filter. If gamma-ray bursts are a filter, they only filter out civilizations that haven't yet reached a certain level of technological sophistication. Once you're advanced enough, they stop being an existential threat and become merely an inconvenience. This suggests that if gamma-ray bursts are responsible for the silence in the sky, it's not because they're wiping out advanced civilizations. It's because they're preventing planets from ever developing advanced civilizations in the first place. They're hitting during the long, vulnerable period between the emergence of complex life and the development of technology capable of surviving the hit. For Earth, that vulnerable period spans from the Cambrian explosion about 540 million years ago, when complex multicellular life really took off, to roughly now a span of 500 million years. If a gamma-ray burst had hit during any of those 540 million years, it would have derailed evolution before intelligence emerged. We got lucky. Or maybe we haven't, and the hit is coming soon, and we're about to discover that the Great Filter is ahead of us after all. There's a darker interpretation of the Fermi paradox that gamma-ray bursts make more plausible. Maybe civilizations do develop regularly throughout the galaxy. Maybe they reach our level or beyond. But they don't survive long enough to become visible across interstellar distances because the galaxy is too dangerous. Gamma-ray bursts, supernovae, asteroid impacts, solar flares. There are so many ways for a planet to be rendered uninhabitable that even technological civilizations don't last more than a few thousand years on average. We've been technological for maybe 200 years, and we're already facing existential risks from climate change, nuclear weapons, engineered pathogens, artificial intelligence, and half a dozen other things we've created ourselves. Add in cosmic threats that we have no control over, and the expected lifetime of a civilization might be very short. If civilizations typically last 1,000 years from the development of radio technology to either extinction or transcendence into something we wouldn't recognize, and if civilizations are spaced millions of light years apart, you'd never see evidence of more than one or two at a time, even if they're arising regularly. They flicker into existence, burn brightly for a cosmic instant, and then go dark. The galaxy could be full of ruins, the remnants of civilizations that lasted a few thousand years, and then succumbed to one threat or another. We might be surrounded by graveyards and not know it because the ruins are too far away or too degraded to detect. This is a profoundly depressing vision of the universe, but it's consistent with what we observe. The silence doesn't mean intelligence is rare. It means intelligence is fragile. On the other hand, maybe we're being too pessimistic. Maybe the threats aren't as severe as we fear. WR-104 might not be pointed at us. Even if it is, maybe the gamma-ray burst will be weaker than predicted, or the ozone depletion will be less severe, or life will adapt more quickly than we expect. Maybe other civilizations have faced similar threats and survived, and they're out there. We just haven't found them yet because we haven't been looking long enough, or in the right ways. The search for extraterrestrial intelligence has been ongoing for about 60 years, which sounds like a long time, but it's a tiny fraction of the age of the galaxy. We've only searched a minuscule portion of the sky, at a limited range of frequencies, with relatively modest sensitivity. Absence of evidence is not evidence of absence, especially when the search has been so limited. Maybe, if we keep looking, we'll eventually find someone. Or maybe the civilizations that do survive gamma-ray bursts and other cosmic threats learn to stay quiet. If the galaxy is as dangerous as it appears, it might be that the smart strategy is to keep a low profile. Don't broadcast your presence. Don't build megastructures that are visible across light years. Stay hidden, stay safe, and wait until you're advanced enough to defend yourself before announcing yourself to the cosmos. This is essentially the dark forest hypothesis, the idea that the galaxy is full of civilizations hiding from each other because making your presence known is existentially dangerous. Gamma-ray bursts don't feature directly in this scenario, but they contribute to the general sense that the universe is hostile and that caution is warranted. Now, let's turn to the question of what humanity should be doing about all this. We know WR-104 exists. We know it's going to explode. We know there's a non-trivial chance it's pointed at us. What, if anything, should we do? The honest answer is not much, because there's not much we can do. If WR-104 exploded right now and sent a gamma-ray burst our way, the radiation would arrive in 8,000 years. But the information that it exploded would also arrive in 8,000 years, so we'd have zero warning. We can't evacuate. We can't build shelters for billions of people. We can't shield the atmosphere. The only things we could potentially do are long-term preparations that would be useful regardless of when or if a gamma-ray burst arrives. We could develop UV-resistant crop varieties through genetic engineering. We could build underground agricultural facilities with artificial lighting that could sustain populations if surface agriculture became impossible. We could research methods for rapidly regenerating ozone using chemical seeding of the stratosphere. We could establish seed banks and genetic repositories to preserve biodiversity through a catastrophe. Some of these things we're already doing for other reasons. The Svalbard Global Seed Vault in Norway stores seeds from crops around the world as a backup in case of agricultural collapse from climate change, war, or other disasters. It would be equally useful in a post-gamma-ray burst scenario. We could expand that concept, create more seed vaults, add vaults for animal genetic material and microorganisms, essentially creating an archive of Earth's biosphere that could survive underground. We could also work on decentralizing our civilization. Right now, humanity is extremely concentrated in cities and dependent on global supply chains for food, energy, and essential goods. A gamma-ray burst would disrupt those supply chains catastrophically, leading to mass starvation even in regions that weren't directly affected by the radiation. If we had more distributed, self-sufficient communities capable of producing their own food and energy locally, the species would be more resilient to global catastrophes. This is something that would benefit us regardless of cosmic threats. It would make us more resilient to pandemics, climate disasters, nuclear war, and all the other existential risks we face. The problem is that these preparations are expensive and require long-term thinking that's difficult to maintain in political systems focused on short-term concerns. It's hard to convince governments to spend billions of dollars on preparations for an event that might happen in 8,000 years, or might not happen at all. Even framing it as general disaster preparedness that would help with multiple threats doesn't seem to generate much political will. We're very good at responding to immediate crises and very bad at preparing for long-term, low-probability, high-consequence events. This is a known failing of human psychology and institutions, and it's not clear how to fix it. What we absolutely should be doing is monitoring. We should continue observing WR104 and other gamma-ray burst candidates with the best instruments we have. Every new observation refines our understanding of the system's orientation and evolutionary state. We should invest in neutrino detector networks because those give us the only possible advance warning of a supernova. We should develop better models of stellar evolution so we can narrow down the timeline for when these stars will explode. And we should search for additional nearby Wolf-Rayet stars that we haven't discovered yet. The more complete our census of potential threats, the better we can assess the overall risk. This is relatively cheap compared to building underground cities or developing ozone regeneration technology. It's just observational astronomy, and the same observations that help us understand gamma-ray burst risks also advance our scientific knowledge of stellar evolution, galactic structure, and a dozen other fields. It's a good investment regardless of the threat level. We should also be thinking about communication and coordination. If we did get a neutrino alert indicating that WR104 or another nearby star had collapsed, what would we do? Who would be responsible for analyzing the data and determining if a gamma-ray burst was incoming? Who would communicate that information to governments and the public? What would the message be? These are questions that should be answered ahead of time, not figured out in the 3 hours between neutrino detection and gamma-ray arrival. There should be protocols, decision trees, pre-written statements that can be adapted to the specific circumstances. This is Crisis Planning 101, and it's surprising how little of it seems to exist for cosmic threats. The broader philosophical question is how to live with existential uncertainty. We are, whether we like it or not, living in a universe where catastrophically dangerous events can happen at any time with little or no warning. Gamma-ray bursts are one example. Asteroid impacts are another. Supervolcanic eruptions, pandemic diseases, nuclear war, climate tipping points. There's a long list of things that could potentially wipe out civilization or significantly reduce human population. Some of these we have some control over. We can reduce nuclear arsenals, mitigate climate change, prepare for pandemics. Others, like gamma-ray bursts, we have essentially no control over. We can't stop WR104 from exploding. We can't deflect its jets if they're aimed at us. We can only watch and hope. This lack of control is uncomfortable, and humans tend to respond to uncomfortable uncertainties in one of several ways. Some people ignore them, reasoning that there's no point worrying about things you can't control. Some people catastrophize, becoming convinced that doom is imminent and giving up on long-term planning. Some people turn to denial, convincing themselves that the threat isn't real or that someone will figure out a solution. And some people try to maintain a balanced perspective, acknowledging the risks without letting them dominate their thinking. That balanced perspective is hard to maintain, but it's probably the healthiest approach. Yes, WR104 might be pointed at us. Yes, it could explode at any time. Yes, that would be catastrophic. But it probably isn't pointed at us, and it probably won't explode in our lifetimes. And even if it does, we'll have had no control over the outcome. Worrying about it constantly doesn't help. Taking reasonable precautions does. Living your life and making plans for the future does. Appreciating the fact that we've made it this far despite all the cosmic hazards is perhaps the best we can do. There's something almost absurdly beautiful about our situation. We're standing on a small rocky planet orbiting an ordinary star in the suburbs of a galaxy containing hundreds of billions of stars. We've been around for a few 100,000 years as a species, which is nothing in cosmic terms. We've been technological for maybe 200 years, and in that brief span, we've developed the ability to understand our place in the universe, to recognize the threats we face, to measure the properties of stars thousands of light years away, and calculate whether their death might be our death. That's extraordinary. We live in the only moment in Earth's history when intelligence has emerged and developed enough to see these cosmic patterns. Before us, for 4 billion years, life existed but was unaware of the larger universe it inhabited. After us, if we don't survive, there might be another intelligent species someday, but that could take another 100 million years of evolution. Right now, in this brief window, we're the universe's way of understanding itself, to paraphrase Carl Sagan. And part of what we understand is our own fragility. We're creatures of biology and chemistry living on a thin film of water and air on the surface of a rock, held there by gravity, warmed by a nearby fusion reactor, protected from radiation by a magnetic field and an ozone layer. All of those protective systems can fail. Some of them have failed in Earth's past. The fact that we're here means they haven't failed catastrophically yet, but there's no guarantee they won't in the future. WR-104 is a reminder that the universe doesn't care about us. It's not hostile, but it's not protective either. It's indifferent. Stars live and die according to the laws of physics. If their death happens to endanger a planet with life, that's just how it goes. There's no cosmic plan keeping us safe, no benevolent force ensuring that intelligent species survive long enough to spread to the stars. We survive or we don't based on chance and our own actions. That's both terrifying and liberating. Terrifying because it means we're genuinely vulnerable in ways that feel deeply unfair. We didn't do anything to put ourselves in WR-104's potential line of fire. We just happened to live at a particular location in the galaxy at a particular moment in time, and that location and timing may or may not turn out to be fatal. Liberating because it means that the things we do have control over actually matter. We can't stop WR-104, but we can try to make our civilization more resilient. We can spread to other planets so that a catastrophe on Earth doesn't mean extinction. We can develop a technology that lets us survive in harsh environments. We can preserve knowledge and biodiversity so that even if we take a massive hit, something survives to rebuild. None of that guarantees survival, but it improves the odds, and improving the odds is the best we can do. Looking at this from a longer time scale, life on Earth has survived 4 billion years of cosmic hazards. There have been multiple mass extinctions, probably several caused by events similar to what we're worried about with WR-104. Life recovered every time. Not the same life, not the same species, but life nonetheless. The biosphere is resilient in ways that individual species aren't. Even if a gamma ray burst from WR-104 wiped out 90% of species including humans, something would survive. Bacteria deep in the crust would be fine. Deep sea vent ecosystems would be fine. Life would persist and eventually diversify again, recolonizing the surface over millions of years. In another 100 million years, the planet could be just as vibrant and diverse as it is now, with no evidence that anything bad ever happened except for a thin layer of chemical anomalies in the rock record. From the biosphere's perspective, these catastrophes are setbacks, but not endpoints. From our perspective as individuals and as a civilization, they're existential. We care about humanity specifically, not just life in the abstract. We want our species to survive, our culture to continue, our descendants to inherit the future. And that's reasonable. But it's worth remembering that the larger story of life on Earth is one of incredible resilience. Whatever happens to us, life will probably continue. That's cold comfort if you're the one facing extinction, but it's a reminder that the universe, while dangerous, is also robust. Complex systems find ways to persist even under hostile conditions. So, where does this leave us? We have a star, WR-104, sitting 8,000 light-years away in Sagittarius. It's definitely going to explode. The explosion might produce a gamma-ray burst. That burst might be aimed at us. If all of those ifs line up, we're looking at a mass extinction event that would fundamentally alter the course of life on Earth. But probably not all of those ifs will line up. Probably the star isn't aimed at us, or probably it won't produce a gamma-ray burst, or probably the burst will be weaker than feared. We don't know. We can't know until it happens. And that uncertainty is something we have to live with. The universe is a dangerous place. Always has been, always will be. We're here because our ancestors survived millions of years of dangers, from predators to diseases to climate shifts to cosmic impacts. We've made it this far. Maybe we'll make it further. Maybe WR-104 will explode tomorrow and we'll discover we were in the crosshairs all along. Maybe it'll explode in 100,000 years after humanity has spread to 1,000 star systems and Earth is just one world among many. Maybe it'll explode and the jets will be pointed 90 degrees away from us and we'll get the scientific opportunity of a lifetime to study a nearby supernova without any danger. All of these futures are possible. We're living in the superposition where all outcomes coexist in potential until the wave function collapses and reality picks one. And when that moment comes, 8,000 years from now, or 8,000 years ago with the information just arriving now, we'll finally know. Until then, we wait, we watch, we hope, and we do what humans have always done in the face of uncertainty. We keep living, keep building, keep pushing forward, because what else can you do? The universe is vast and old and dangerous and indifferent, but it's also full of wonder. And we're part of that wonder, standing here on our little world, looking out at the stars, understanding them, fearing them, marveling at them. WR-104 is out there, spinning, dying, aimed somewhere. We're here, watching, wondering, hoping that somewhere isn't here, and somewhere in that tension between knowledge and uncertainty, between danger and hope, between our fragility and our resilience, is the story of what it means to be human in a universe that doesn't promise us tomorrow, but gives us today. That has to be enough, because it's all we have.